Good afternoon, everyone, or good morning to people in California off the West Coast. Thank you all for attending this. Today I'm going to talk about the effect of urban trees on air quality. And as Meredith said, if you have any questions throughout this, there's plenty of time. This is a brief introduction to this topic. Feel free to give the questions throughout the presentation here. So I'm going to start with is just an overview of why or how the impact of air quality in general. Then we'll talk about the impact of trees on air quality. Okay, so the main issue with air quality is it's a problem in many cities due to the combustion of materials and fuels and things like that, is that it leads to increased respiratory symptoms. We have hospitalization for heart and lung diseases and often premature death. And you can see it's not only affecting humans, but you can see in this picture, this is a picture of the tulip poplar. It also affects vegetation. This is in that slide there on the lower left here. The pointer's working. Is typical ozone damage you'll see on plants that are sensitive to ozone, because ozone is a highly reactive gas that will damage tissues. Not only does it affect people, but it also affects plants and materials throughout cities. So we're talking about air pollutants in cities. There's 5 or 6 main pollutants that we're concerned with. First of all, there's particulate matter. There's PM10, which is particulate matter less than 10 microns, and which was the old EPA standard. The new EPA standard is now PM 2.5, which is particulate matter less than 2.5 microns. Particles are physical mass, and it's going to be important in understanding the roles of trees as compared to when we talk about gases. Now, under gases, there are primary gases and there are secondary gases. Primary gases are directly emitted from a source. In this case, we're talking carbon monoxide from automobiles. As one of the sources, nitrogen oxides or nitrogen dioxide, NO2, which are mainly due to high temperature combustions. Anything that burns fuels at high temperature will produce nitrogen oxide. Sulfur dioxide, power plants and diesel fuels produce sulfur dioxide, but they're primarily emitted from the tailpipe or from the source itself. Secondary gases are not emitted by anything but are formed through chemical reactions. So ozone is not emitted directly by any one source, but it's formed through reaction. And this becomes important understanding where it's coming from. So when we try to design urban forests, the impacts will differ for each of these, or the mechanisms and the impacts will differ depending on which pollutant we're talking about. So just briefly review for those that couldn't hear me, there's main type of pollutants are particulate matter, which are particles in the atmosphere, particles less than 10 microns or 2.5 microns. We have primary gases that are directly emitted from the source, carbon monoxide, nitrogen oxide, sulfur dioxide. And then we have secondary gases that are not emitted by any one source, but are formed through chemical reactions. This slide illustrates what we're talking about with PM10 versus PM2.5. These are very fine particles in the atmosphere. You can see the grain of sand, a human hair. And within the human hair, you have particles that are PM10, less than 10 microns. And within the PM10 micron, you have PM2.5 microns. What's important here is the PM2.5 microns are very fine particles that are often formed through either through chemical reactions or directly from combustion, from automobiles and things like this, from plants. There are forest fires and other sources of PM2.5. These particles, because they're so small, tend to stay entrained in the atmosphere for long periods of time. They don't settle out like larger particles. And the other problem with these fine particles is that they can be taken up into your nose passage into your lungs. Because they're so small, they tend to go deeper into your system. They're more important for terms of human health impacts. So I'll give you an overview on the particulate matter. The other one that's important to understand here is ozone. People get confused on this sometimes. There's stratospheric ozone and there's tropospheric ozone. The stratospheric ozone is very high in the atmosphere. It's a very thin layer that protects us from ultraviolet radiation. So when we talk about thinning of the ozone layer, that's very high in the atmosphere, up around 7-8 miles up in the atmosphere in the stratosphere. Tropospheric ozone is ground level ozone, and this is a common component of smog. What we're going to be talking today about is ground level ozone, the smog components in the ground that we breathe. Same chemical, but in different positions. You can see on the left-hand side there in the EPA document, ozone bad nearby, which means you don't want it in the smog, but good up high to protect you from ultraviolet radiation. Again, same chemical, but we're talking about tropospheric ozone here. Another thing to understand that's important for urban forestry is the Clean Air Act. The EPA requires has set, or EPA sets national ambient air quality standard levels for pollutants. States must meet these air quality standards, and they set up state implementation plans to do so. We'll talk about that a little bit later coming up. But they set primary standards, which are set to protect human health, such as sensitive populations for children and elderly. And they also have secondary standards, which are for public welfare against damage to animals, crops, and vegetation. I'm going to show you some of the statistics from the United States that for some of these national ambient air quality standard levels. First is to show you that in terms of how the air is getting cleaner, in the past 30 years, you can see, based on the EPA standards that they've set, carbon monoxide has gone down by 82%, ozone by 28%, lead by 90%, nitrogen dioxide by 52%, and sulfur dioxide by 76%. And you can see recently in the last 10 years that the particulate matter has also gone down by about 30%. So the air quality is getting much better in terms of the air in our nation. However, there's still air quality problems that exist, and the role that vegetation can play in this improving air quality is what we're going to discuss today. Number of people exposed for PM 2.5, this fine particulate matter, 74 million people in the United States are exposed to that in areas that do not meet the national ambient air quality standard levels. So they're in what are called non-attainment areas. For particulate matter less than 10 microns, it's 29 million people. Sulfur dioxide, 1.2 million, and ozone, 123 million people. For carbon monoxide and nitrogen dioxide, they're actually, once you reach attainment, you go into what's called a maintenance state implementation plan. And so for nitrogen and carbon monoxide, there are areas of the country that are in maintenance, but actually technically have met attainment and are now trying to maintain attainment. So I'm going to show you some of the maps coming up. Just, some people are in different areas. You can see how these pollutants are distributed. This is the map for PM 2.5. I focused some of the numbers here because this is a presentation through Utah, the amount of people that are exposed. You can see the regional variation, California, New York, Ohio, Michigan, but parts of Utah also have this. And in Utah, we see 2.3 million people exist in areas that have non-attainment areas for PM 2.5. For PM10, most of the non-attainment areas are to the west, and again in Utah it's 1.6 million people are in non-attainment for PM10, which is particularly not less than 10 microns. Sulfur dioxide, non-attainment areas, you can see them scattered about, again mainly in the west, a little bit in Pennsylvania there. 1 million people in Utah. And the last map, because these are just non-attainment maps for the United States, not the maintenance areas. Ozone, you can see ozone is well scattered about throughout the country, but in Utah there are no areas that are classified for non-attainment. But you can see California has some very significant non-attainment areas in the Central Valley there in Southern California. So a lot of people are affected by pollutants in many different fashions. So the question is, in the main part of this presentation, what's the role of urban forests in improving air quality in our cities? Before I get to that, I want to talk a little bit about urban forests in general. Again, I threw up here state statistics. There are information for every state in this country if you wanted to see the cover data. I just pulled up Utah in this case. Nationwide, tree cover in the United States in urban areas, tree cover in the United States is 34.2%. Tree cover in urban and community areas is about 35.1%. And in rural areas, it's about 34.1%. So in essence, urban areas actually have more tree cover nationwide than the rural areas do. But the distribution does differ across the states. But you can see in Utah, urban areas are about 16.4% tree cover. So trees are a significant component in urban areas in the United States. And you can see nationwide, of the total state tree cover, about 5.5% comes from urban areas, but in Utah it's 2.5%.
Dr. Noack, we had a question here.
And we're talking about...
Yep,
sure.
It was about, just kind of back to your last slide about the non-attainment status, and the question comes from Kent Holm about other non-health related consequences of being a non-attainment status.
Non-health related consequences. Well, there's two that would go back to the secondary standards. There's material damage that could be caused by pollutants, depending on the pollutant that's involved. There's material damages to plants and crops, which is that secondary standard the EPA is talking about versus human health. But on the other side, there's an economic disincentive, I guess, or if you don't reach attainment, there are economic, basically, sanctions against those communities or areas that are in non-attainment, because the EPA regulates this. So there's an economic driver as to why you want to be in attainment, mainly for human health and the health of vegetation, crops, and materials within the non-attainment areas. But if you don't reach attainment through the state implementation plans in the Clean Air Act, the EPA comes down to make sure you get into containment. So there are economic, in essence, penalties, actions that happen if you do not reach attainment. Is that what was meant by that question?
I think you covered it. Thanks.
There we go. Yep, okay, thanks. Yeah, feel free to ask any questions. So we have a lot of trees within urban areas. Again, about 34% of the United States is covered with tree cover, about 35% within urban and community areas. Again, urban and community is defined by the census. Urban defined by population density, typically areas of about 500 people per square mile, and communities are based on political definitions of communities. So the two combined make up the urban community land, which is about 5.2% of the United States classified as urban community land. Now within the tree cover, this is an interesting statistic. Typically, tree cover, if you live in forested regions of the United States, say the East Coast and parts of the West Coast, where you have forests as natural vegetation types, you typically have tree cover around in urban areas about 40 to 60%. In grassland, areas that are typically grassland, tree cover in urban areas is about 20% overall, and in deserts, it's maybe around 10 to 15%. So ecoregion, where you live, is a main driver of how much cover you have within your city system. What this graphic shows is how the cover is distributed within the city itself. So you can see if you live in a city that's forested, typically about 43% of your total canopy cover comes in residential areas and 37% comes from vacant areas. And what's interesting, in forested regions, trees naturally regenerate quite frequently. So if you have vacant land, you'll have natural regeneration occurring. So the shift here, what's interesting to show on the graph is how this shift between residential and vacant land changes as we move from cities and forest, to city and grasslands, to city and deserts. Because this is a strategy of how you're going to increase canopy cover, or where the canopy cover is in terms of trying it. You're going to use trees to improve air quality. How are you going to get the trees in? So in forests, 43% of your forest cover, tree cover, comes from residential, 37% from vacant. When we move to grassland areas, 54% of your cover is in residential areas and only 20% in vacant areas. And then when we move to deserts, 72% of your cover comes from residential areas and only 2% from vacant. Because when you're in a desert, very few trees regenerate in vacant areas unless you're, say, along a stream area. In grasslands, again, you need the water. So vacant lands become much more important in forested regions to provide regeneration or forest cover, because you have that regeneration. When we move to deserts or more grassland areas, those residential landscapes where people are planting trees become more significant in terms of the urban forest benefits. I'm just waiting to see if there's any questions. Okay, so the question becomes, there's a question here, where does public right-of-way fit into these categories? Okay, public right-of-way would fit against which land use the public right-of-way is adjacent to. So many public right-of-ways are in residential areas. If you had a street tree in a residential area on the right-of-way, it would be classified as residential. So we didn't separate out the right-of-ways except for the land use to which the land use was adjacent to. So there's not a separate category there. So we have these trees in cities. Again, 35% of the area covered. It depends. It distributes differently by land use depending on where you are in this country. But the way to look at this, now I'm going to talk about the tree's effects on air quality. There are many different species in many different configurations, and the impacts that these trees have are based on a couple things. One, these trees produce a physical mass. They have wood, they have leaves, and that's important in understanding. We'll show this in terms of the trees and air quality. They also exchange gases, which, because they have the leaves, we have a gas exchange process going on, which is also important. So it's how do we design these physical elements in the landscape to maximize the effects on air quality. In order to do that, we have to understand how these trees are influencing air quality. To do this, and haven't even heard me talk before, I've been talking about this on years, but we have new data in this presentation here. I use the acronym, or mnemonic, how do you say that, device, of TREE, T-R-E-E, and each one of these represent one of the aspects of how trees affect the environment. So first we're going to talk about temperature reduction. This is one of the most important aspects about trees and air quality. Again, the leaves have, on the other side of the leaves, there's many of these stomates. These stomates open up during the daytime to evaporate water, to allow gas exchange to occur. But when they open up, water is evaporating from the process, and evaporation is a cooling process. So these leaves are very important in terms of temperature reduction. Also, trees provide shade, either through the bark or through the wood itself or through the leaves. But what's important in this aspect is what you want to do is maximize healthy leaf surface area. And because of these stomates and this gas exchange, you want healthy leaves and you want water being moved through the system. This is not so much a problem when we're in forested environments where water tends to be abundant. This can be an issue in more desert landscapes where water is not that abundant. What you get in terms of this temperature reduction is you have what are called urban heat islands. So as we move from a rural landscape to a more urban landscape, we tend to reduce canopy cover and we tend to increase impervious surfaces. In doing so, we tend to have increased air temperatures within the city cores. This has to do with many factors. One is the loss of canopy cover, which is we lose that evaporative cooling that's going on. The other, if we bring in more impervious surfaces, they tend to absorb heat and re-radiate the heat back, so they act as heat sinks in many ways to the urban area. The greatest temperature differential in terms of urban heat island occurs just after sunset, between the temperature difference between rural and urban lands, because when the sun goes down, these impervious surfaces have absorbed the heat during the day and re-radiate that heat back. And just after sunset, the rural areas tend to cool down rather quickly, while the urban areas tend to stay warm. But we have these impervious surfaces that create warmer temperatures. We have loss of evaporative cooling and shade from the trees. We also produce combustion, which produces heat within cities. So we tend to get warmer air temperatures. Temperatures are important for pollution because many pollutants are temperature, the emissions are temperature dependent. This graph illustrates, in terms of ozone, the temperature dependence, particularly with ozone, is that as temperature gets warmer, in this case in Los Angeles, we tend to have more and more ozone formation being formed. Because what happens when you get warmer temperatures, you tend to get more emissions, because many emissions are temperature dependent. You also have altered photochemistry. So as you have warmer temperatures, the formation, remember ozone is a secondary pollutant, the formation of this ozone tends to accelerate due to warmer air temperatures. So if you can cool the temperatures down, we tend to have less ozone and less emissions. Also, what tends to happen when you tend to get very warm days, you tend to get very stagnant days. So if you don't have any wind moving, the pollutants tend to build up because you don't have a dispersion from the wind, which is also tied to very warm temperatures. Tied to temperatures and meteorology is also a thing called boundary layer height, which is the top of the atmosphere in which mixing occurs. And you can hopefully see in this image that brownish haze layer where the smog is being formed, and above it is blue. What happens is the height in which the atmosphere mixes becomes very important in terms of concentration. So the height of the box, this boundary layer height, is important, because if I compress that box down and make it lower, I will increase the concentrations. And look at it this way. We try to show this to some of the classes we teach at. If you were standing the size of the box is important, and trees affect the size of the box because they affect wind speeds. If I reduce wind speed, the top of the box, because you'll have less mixing, will tend to shrink, move the box down, which means there'll be less space for that pollutant to mix. What this diagram is trying to illustrate is if you had to stand in a box, and basically what in this case you're breathing in air in that box, you have a couple things going on, which are very important in terms of understanding the concentration of the atmosphere. One is from the upper left there, that pipe coming into the box is the amount of pollutants coming into the box. Or in another example you could say is maybe water in a box. The pipe at the lower right is the movement of the pollutants or water out of the box. So in essence, if I had to stand in a box that was filling in with water, I'd want that pipe on the upper left to be as small as possible. I'd want that box at the lower right to be as big, or the pipe at the lower right to be as big as possible, and I want the box as big as possible. In essence, because you want more of that water, or in case we're talking pollution moving out of the box and coming into the box. And if you don't have that, you want to be in as big as a box as possible. So the pipe coming in is basically the emissions that are coming into the system. The pipe going out is how much is being removed by the system. That's what we're talking about in some cases of the trees. And the size of that box is very important in terms of what the concentration that you're breathing in. Another way to try to explain this is if you had 1,000 killer bees that were going to be released in a room, would you want to be standing at a phone booth, or would you want to be standing in the Superdome to release those bees? I'd prefer to stand in the Superdome, because if I have the same amount of bees and they're dispersed over a large area, there's less of a concentration, less of likely to be stung by that bee. If I'm in that phone booth and release those bees, the concentration is much higher. So the size of that booth or that box is very important. And trees influence the size of that box because trees reduce wind speeds because they act as roughness elements, and that's one of the negative aspects about it, because the trees will actually reduce the size of the box and actually tend to lead to in concentrations in that case. So that's the meteorology. The positive side, you have temperature reductions, which are very important because they affect emissions. It can reduce pollution, but you also have reduced wind speeds, which can reduce or increase concentrations. On the other side, we have trees removing pollutants. Again, those stomates, when they open during the daytime because they're evaporating that water, what happens is you have more pollutants on the outside of the leaf than you have on the inside. So basically you have a concentration gradient moving from the outside of the leaf to the inside of the leaf. And inside the leaf, there's a lot of water. A lot of these pollutants dissolve in water. So that's why we want to have a lot of active leaf surface area out there that is functioning and exchanging gases, because you want those pollutants to move from the outside of the leaf to the inside. The trees are very good at removing ozone, and ozone, as you saw, depending on the plant and how sensitive the plant is, you can get damage to the plants. They're good at removing sulfur dioxide and nitrogen dioxide, and when those pollutants move inside of the leaf, they dissolve in the leaf and actually form a nitric or sulfuric acid. In that case, the pollutant breaks down, but actually the nitrogen and sulfur can actually act as a fertilizer to the plant. So it's not harmful to the plant generally, unless the concentrations are very high and it forms a very strong acid. Then you'll start seeing the leaves burn. If you start seeing the leaves burn because you have that much sulfur dioxide or nitrogen dioxide in the atmosphere, you've got other problems that you have to deal with, because that's very high concentrations. But typically, the air pollutants will actually act as a fertilizer. Carbon monoxide, which is the other gaseous pollutant, can be taken up by the plants, but they do it at a very low rate. They have adopted to take in carbon dioxide, which is a greenhouse gas, but they don't take out carbon monoxide very well. The carbon monoxide would not be harmful to the plant. It actually can act as a sugar source for the plants if the plants can take it out. So that's the mechanism of removal, is at the leaf surface for the most part. There's some surface removals by the bark and in the surface of the leaves, but most of the gases are removed from the interior of the leaves. So you want to have those active, healthy leaves out there exchanging the gases. Particulate matter is a different case. Because these are particles, again, these are the PM10, the PM2.5, the removal mechanism is at the surface of the plant. And this is where we step back. If you're on gases, you want to have a lot of gas movement going on. So you want to have these trees that are moving water and transpiring the gases. If you're designing for particles, you want to have plant surfaces that have a texture and the plant composition that can allow the particles to stick to the plant surfaces, the leaves or the bark, and stick and retain to those leaves. So Sticky leaves are very good at removing particles. Hairy leaves, leaves with surface textures, leaves that tend to be smaller and multiple leaves, which allow air to infiltrate into the canopy so they can impinge on the surface. Again, these PM 2.5s tend to stay in the atmosphere a very long time. You want to get them to that plant surface. So you have to have the wind moving. It hits the plant surface and can stick to the plant surface. Now the problem with this is that they're only temporary storing sites for many of the particles, because what can happen, think about it if you're wearing clothing. Clothing is the same type of, can also remove particles. And depending on the texture of your clothing, some particles or some clothing is better for removing particles than other clothing. Camel hair jackets are probably very good with more of a texture surface to removing dust than, say, a smooth surface shirt. But if you do get a dirty shirt, what do you tend to do if you want to get the particles off? You tend to shake it outside. Well, the same thing happens with leaves. With the wind moving on, the leaves are constantly, especially in high wind events, are being buffered about. So many of these particles can be resuspended back to the atmosphere. And again, so there's this constant process of particles moving to the surface and then particles being resuspended due to the wind. On the other side, if you think about it, if now you have this jacket that's all dirty, you shook it outside, what do you want to do to get it clean? You wash the jacket. What happens, rain is a good mechanism by which particles can be washed off these plant surfaces and then moved to the ground surface. Some of these particles, I'm just looking at Andy's. Hi, Andy. Honeydew-coated linden leaves remove more particles. That's because they are sticky. And that's what you get. The honeydew will actually, the aphids which produce the honeydew, produce a sticky coating to the leaves and will remove particles. So you can thank the insects for that. So the washing of the particles becomes very important. So you want to get those particles into the soil. It's washing. Many of the particles are water soluble and they dissolve and are taken out of the atmosphere. Some of the particles are not. And this is important to understand. Some of the particles, say heavy metals, do not dissolve in water. They're washed off the leaves and go to the soils, or when the leaves drop, they're on the leaf surfaces or in the leaf surfaces and they decompose and go into the soil surfaces. So often for particulate matter, trees can remove many of them by intercepting and then have the water dissolve it. But for heavy metals and things like that that don't dissolve in water, they act as a transfer mechanism of moving it from the air into the soil. So it's not necessarily out of the system. It says transfer so we don't breathe it in. But then we have another issue, possibly with soils in that case. So again, we want to have in that box diagram more of these surfaces out there to take the particles out of the atmosphere, and in some cases smaller pipes coming in so we have less of these heavy metals in the first place. It's best not to have the particle emitted in the first place. The emission controls are very important. Once it's in the atmosphere, there are few surfaces that are active removals of gases, and the few surfaces are plants through transpiration and humans through breathing. So we want to design so these plants are exchanging the gases more than we do so they can clean the atmosphere. For particles, on the other hand, most any surface out there, to differing degrees, will remove particles, because some particles will adhere to building surfaces, to plants, to people, and things like that. So it's how do we design our urban forests or urban landscapes to remove more of these pollutants. What this graph just shows you the illustration. It's a time series of a paper we just did looking at PM 2.5. And you can see this is what the graph is showing, the amount of, it's called cumulative flux, but the amount of particles that are on the leaf at any one point in time. And you can see it fluctuates through time, and it has to do with wind speed. There are times when the particles become very high on the surface of plants, or times when it goes relatively low, either due to resuspension, or you can see on the upper part of that graph, when it rains, the particles on the leaves are washed off and then moved to the soil surface, and then after the rain, because the leaves are refreshed, they tend to pick back up more particles. So there's this whole process going on in terms of removal of particles. Here are some, these are new estimates just came out in the last few months of looking at PM 2.5. This is the new measurements. We've never had this assessment before. In the past we've always looked at PM 10. Now we're looking at these fine particulate matter. And we can see in the various cities there, the pollution removal varies in tons per year from about 5 tons in Syracuse to up to about 65 tons in Atlanta. But you can see the values vary. I'm going to show another slide on the value coming up. The greatest value for this PM 2.5, this fine particulate matter, comes from New York City. The second is Chicago, and third is Los Angeles, even though they don't have the greatest removal or the greatest change in concentration. Why that is, it's important to consideration of where we plant trees and why we design trees for human health is. In New York City, Chicago, and Los Angeles, there's more people per unit area, there's higher population densities. If we plant a forest in the middle of a rural area with no people around, the forest will remove a significant amount of pollution, but there's nobody there to receive the benefits in terms of human health. What this is showing in terms of value is, in terms of, say, Manhattan or New York or Chicago, the values tend to be highest in these urban areas where there are more people, because there's more people receiving the benefits of having improved air quality. And I'm going to show you that on the next slide right here. This table shows the human health effects from the reductions in PM2.5 concentrations in those 10 cities. What we did in this study was looked at the effect of trees on PM2.5 and then tied it to an EPA model called BENMAP, which looks at human health statistics and the lowering of incidences due to improved air quality and lowered concentrations. What we found, the biggest value is derived from reduced human mortality. And on average, we found about 1 human life per city in these 10 cities is saved per year due to having improved air quality from PM2.5. But you can see if you go down to New York, which is lower center, there's almost 8 people per year lives are being saved because we have improved air quality. And that's valued at about $60 million per year. Question just came up, where did you say this table came from? What agency? This table is in the paper that's cited at the bottom of the slide in environmental pollution that just came out. The data for human health actually came from a model that we ran called BENMAP, B-E-N-M-A-P, which comes from the US EPA. And we ran BENMAP, we actually run it for the whole country, but we ran it for these 10 cities also. So the process that we used iTree to estimate the pollution concentration changes. We fed that into the BENMAP model to estimate, based on the population for those cities, the human health impacts. Because the health impacts are dependent on who's receiving the benefits. How many people? So New York has more people, but also the age distribution, because certain people are more susceptible and have more health incidences depending on what the pollutant is. So you can see there's bronchitis, asthma, hospital admissions, mortality. So that paper's out. We have another paper coming up I'm going to talk about in a second, which we're doing the whole country right now for all the pollutants. And I'm going to show you some preliminary results next on the next slide. What this graphic shows here is the differences, the relative differences based on tree size and the relative differences based on the type of pollutant. So you can see again, trees do their best at removing ozone and particulate matter, followed by nitrogen dioxide and sulfur dioxide, and then finally carbon monoxide. But you can see if you have a tree less than 3 inches in diameter versus a tree that's greater than 30 inches in diameter, a large tree will remove about 60 to 70 times more pollution than a small tree. This is important when you're trying to swap out trees, that if you lose one large healthy tree out there, you're losing basically the services of 60 to 70 small trees. That it would take that many to be comparable for the same amount of pollution removed. These are the latest numbers we have on national air pollution removal. This is the paper we're working on right now. We estimate about 668,000 metric tons of air pollution are removed annually. It's worth about $6.3 billion per year just in the urban areas alone. Most of that removal and value comes from ozone and PM2.5, because that's where most of the impacts that we have on estimates in terms of mortality. On a city level scale, it's millions of dollars per year per city, depending on how big your city and what your tree cover is. Percent air quality improvement is typically around 1% due to pollution removal. It can be as high as 15%. It's interesting to note in this paper that we're working on, it's not out yet, in terms of national pollution removal, most of the pollution removal, over 90% nationwide, let me step back. So there's 20 million metric tons being removed per year, 21 million metric tons being removed per year. About 20 comes from rural areas. Only about less than 1 million metric tons per year come from urban areas. But about 2/3 of the value comes from that urban area, because that's where most of the people reside. So again, it's tying to the impacts to where the people are is very important. The percent air quality improvement is an important point I want to make here. So typically about 1% air quality improvement, but in terms of design, this becomes important. So trees remove 686,000 tons of air pollution in urban areas of the United States. Now, when we get to designing urban forests, we know there's differences among species because ones that remove water will tend to have greater gas exchange, and differences among species, among texturedness of the leaves and how much pollution is being removed. But what's also important in the design when we're getting down to actual urban forest management is what I call source-sink relationships. Is where's the pollution coming from? In this case, in this illustration, we have cars driving through a heavily canopied street. And where are the receivers of the benefits? Where do the people reside? This becomes very important in terms of design because in this case of an illustration, if you have a heavy traffic load under a heavily canopied street, these trees are actually preventing the dispersion of that pollution in many cases and keeping that concentrations relatively high near the ground level. Not that big of a deal if you don't have a lot of traffic, but if you have a major street corridor with a lot of traffic that tends to sit and you have it sitting, it's like sitting in a tunnel. If you can't get that pollution to disperse, you're going to end up having higher concentrations. And the people that walk along those streets are going to tend to be breathing in those higher concentrations. So what we want to do is design urban areas which have these mix of roadways that go through them that allow, particularly along major roadways, say freeways, you want the vegetation along the sides not over covering the roadway so that the pollution can go up and disperse into the atmosphere. Because of the old adage, the solution to pollution is dilution. We want to get that concentration to drop. In essence, what you're doing in this case along the street is you're reducing the size of that box. It's no longer mixing to the height of the boundary layer. Probably most of it will be mixing beneath the canopy itself. So you've then put yourself in this phone booth type situation where you tend to have higher concentrations, unless you can force wind through that to disperse that out. On the other side, the advantage of doing this, the trees will be very effective, or will be more pollution removal will occur in this area because the concentration is higher. But because the concentration is higher, people will be breathing that in more. So the point here is we need to consider when we're planting trees is where is the pollution coming from, whether it be a roadside or a factory, and where the people are. Best case you'd want to do is keep people away from the roadside, so that's because that's a source of many of the pollutants. Protect them, maybe build a buffer of vegetation along the side of the roadways to keep the pollution from moving sideways into where the people live, and put people within canopied stands. There was a study in Los Angeles in the San Bernardino Mountains where we estimate maximum effective pollution removal from trees maybe at 1% on average, peak effects around 14 or 15% from trees. Their study in the forested stands around Los Angeles found peak reductions in ozone at around 40%. Now the question is, if the removal is only accounting for 15% of it, where's this extra 25% coming from? It has to do with ozone moving into the forested stands from above, this is our theory, and that because the stands are protecting you, it's like having a roof over your head, the ozone's not getting down into the interior of the stands. So if you stand in an interior of a forest stand, a lot of the particles drop out, a lot of the pollution, if there's no source interior of the stand, the pollution's coming in from on the top, can't get to the lower level that easily. The interior of the forested stands are fairly clean. However, if you drive your car through those forests, you then are putting the pollution right where the people are breathing. Question here, please discuss how canopy impact in reducing temperature offset source sink relationships you just talked about. So temperature impacts. Temperature will feed back into this. Because along the street side, temperatures will be reduced. They'll be much cooler along this roadway here because of shading of the surfaces, so the road's not heating up as much, and plus you also have this evaporative cooling. One of the factors which I'll come up talking about next is going to be energy effects. If you live in this forested area, you'll produce less energy, you need less energy use during the summertime, so you reduce emissions. The roadways is probably going to be evaporating. So these roadways will actually volatilize some of the chemicals depending on how fresh the tar is. You might have reduced emissions of these volatile compounds from the roadways, the smell of the tar. Parked cars, because they're not perfectly sealed, at least the old ones with the carburetors, would actually evaporate gasoline. So you'd have some emissions coming from cars also. So temperature will feed back somewhat. You might have more fuel efficiency from the cars also that are driving through. So you'll get some reduction in emissions because it's reduced temperature, but if you have a lot of cars going through, it's still the mass source of these cars that will produce a lot of these emissions. So again, you have to know how many cars are going through the area, which is important in terms of the emissions. Number 3, emissions. Hey, Naomi. Hi, Naomi. Switzerland. New York City is losing its mature trees. If the trees with the greatest leaf surface area at allowing right, the Million Tree Planting Initiative disguises these removal by increasing quantity, not quality. How can we change the way we inventory trees so that we quantify leaf surface area? Well, basically, to get at leaf surface area, iTree does that. If you measure the crown canopies, size is a proxy. DBH is a proxy for leaf surface area, unless you measure the crown itself. The condition is very important. I can have a very large tree that's dead and have no leaf surface area. So you want to take into account condition, crown area, and if you can't measure the crown area, then condition along with DBH would be a proxy for leaf surface area. But leaf surface area, quality leaf surface area is important. Emissions we need to consider: trees emit volatile organic compounds. If you smell a pine tree, you smell a rose, any fruiting structure, they emit volatile organics. These volatile organics are very important in terms of ozone formation. They're one of the contributing factors. Gasolines and other volatile organic. Paints have volatile organics. If you mix volatile organics with nitrogen, you tend to get ozone. It's this process of formation. This is why Ronald Reagan had that quote about killer trees and things like that. Trees do emit volatile organics. They do. Some species have very low emissions. Some species have very high emitters of isoprene and other chemicals. So the idea is you have to understand that there are negative aspects besides the reducing of the boundary layer height, but also various species can produce more volatile organics into the mix. So species selection becomes very important in terms of volatile organics also, in terms of different species making differences. Emissions are temperature dependent. Certain chemicals go up during the daytime. That's when ozones form the most, but these plants also give off more volatile organics. It's light and temperature dependent in this process. Not only do trees give off emissions, but what we do as managers make a difference too. The more we run our chainsaws and do things, we have to consider our process, because we're also contributing to the emission process through maintenance. So the more we can do less emitting maintenances using through the combustion of fossil fuel, the better off we'll be in this whole system approach. Okay, lastly, energy conservation. This is pretty straightforward. If we plant trees that reduce temperatures, shade buildings, block winds, we can alter building energy use. In the summertime, it's generally a positive effect, because shading buildings in the summertime and cooling air temperatures tend to reduce our need for air conditioning. In the wintertime, it can get a little dicey in some fashions. If we shade our building in wintertime, even trees out of leaf can produce 35 to 40% shade. We tend to increase energy use in the wintertime. So we have to be very careful if you're more northern climates of how you design. But if we design such that we can reduce energy use in buildings, we then can reduce emissions from power plants, because the energy that's produced to cool or heat our buildings also leads to emissions from power plants. These are some estimates that we have nationally. We're working on newer ones to update these values, but it can be quite significant in the billions of dollars annually that we can have in avoided energy production and avoided carbon emissions from the power plants, because we've put trees in smart positions around buildings to reduce energy. Again, due to shade, due to temperatures. We reduce the emissions, or reduce energy use, we reduce the emissions from the power plants. It's not only related to CO2, just one other slide here. As temperature goes down, we reduce the demand from the power plants also. But this is not also related to CO2. You can see in this graphic, these are emissions of utilities per megawatt hour, which is electricity, and per million BTUs, which are related to heating. You can see carbon dioxide, which is the dominant greenhouse gas, is the dominant emission. But you also have emissions of sulfur from power plants and from burning of the fuels, nitrogen oxides, methane, nitrous oxide, particulate matter, carbon monoxide, and VOCs. So by reducing our energy use, it's not only conserving, reducing or avoiding the emissions of carbon, we're avoiding the emissions of other pollutants in the first place. Again, we're reducing that pipe that's coming into the box of having less emissions in the first place. So planting trees can increase the amount of pollution that's being removed, and if we do it smart, we can also reduce the amount of pollution that's being emitted in the first place. So those are the 4 factors. We do, in iTree, temperature reduction is a new model we're working on. We have removal, we have the emissions of volatile organics, and we have energy conservation already estimated. We're trying to have people put this all together. And there have been some studies that looked at this. Generally in Los Angeles, this is for ozone, it was found that, this is from Hyder Taha, if you increase tree cover in Los Angeles, you tend to have reductions in ozone if the trees were low VOC emitters. So in Los Angeles, you wanted to avoid those 9 species that I showed earlier that were high VOC emitters. If you just increase generally with the mix, you tended to get increases and decreases across the basin. So in the case of Los Angeles, species selection was very important. We did a similar study for the New York northeast coast area. What was interesting here is we found that adding tree cover in the New York metro area reduced ozone, particularly downwind. But what was critical here, it was the physical effects of the trees that were important, which was the pollution removal, the air temperature reduction, and the changes in wind speed. It was not the VOC emissions hit, because there's so much VOCs. Unlike Los Angeles, where VOCs are very important, it's the physical dimension of the forest, having that physical mass out there that is cooling the air temperatures, that it's removing pollution, that it's changing the meteorology, becomes very important in terms of reducing ozone. And the general trend is more trees tend to reduce ozone, but we need to be careful on the species selection, particularly if you're in areas like Los Angeles. The other thing that was interesting, we did a study of increasing tree cover in New York by 10%. We found a 4% or 4 part per billion reduction, which is quite significant, of having increased of tree cover on ozone. What was interesting, though, is if we increased tree cover to 30%, the answer was almost exactly the same. So there's some diminishing return in terms of reduction of ozone. That 10% got you 4 part per billion reduction in maximum ozone. 30% got you about a 4 part per billion reduction in maximum ozone. So there's this tending effect which leads to temperatures or removal, that there's a diminishing return. Where that level is, we don't know exactly. For New York, it's probably somewhere between 10 and 30. What was interesting, though, that 10% increase in canopy cover in New York City was very significant. It was a 3% reduction in peak ozone, and it was 37% what was needed to gain attainment for New York, the New York metro area, just through that canopy program. Okay, here's a question here from Chris. Are there particular low VOC emitters that you would recommend? How many high do you? Okay, there are low emitters. There are many low emitters, Chris. We have papers on that in some of the reports. They're online. I would not recommend any one of them. I would recommend ones. My selection would be, I would always recommend a tree that survives and does well in your area first, regardless of whether it's a high or low emitter. Oaks are a high emitting species, but if oaks are one of the very few trees that survive and do well in your area, and same thing with platanus, the plane trees or sycamores, I'd rather have a tree, regardless of its emissions, that performs well and can live a long time in an urban area. Outside of that, there are many species you can choose from that are low emitters. Maples are low emitters, and you have to look at the list. Pretty much if you're not on that top 9, you're probably okay. Many of the high VOC trees you listed were very large trees. That's true. Yeah, there are large. Maples are one that are out there. So you have to go through the general. Those are just happen to be big ones on that list. But there are other ones that can be used. Pretty much if they're not on the list and they're big, they're probably okay. And Naomi says, in your calculations of 10% increase in urban tree cover, what's the consideration of tree size, leaf surface area? This was basically based on cover. It wasn't tree size. It was basically, we assumed the leaf area index, which is the depth of the canopy, would stay about the same. So in our estimations, it would be the same composition that you have today, pretty much, your distribution, which are mostly, in terms of number of trees, most 50 to 60% of most forests are less than 6 inches in diameter. The rest, and it diminishes. You have fewer and fewer trees as you get to larger and larger diameters. Okay, lastly, just last couple slides. Trees will impact air quality. For the most part, they will impact it positively, and if you do it right, you can pretty much assure you'll have a positive impact. As part of the Clean Air Act, which we talked about earlier, there are state implementation plans if you're in non-attainment areas that have to be filled out by the states to meet attainment. So these state implementation plans establish the rules and regulations and have legal authority. And this is very important because states have to submit these plans. If you're in some of those areas on the maps that I show you that are non-attainment, state implementation plans are being done, or even if you're in attainment, the maintenance state implementation plans are being done. The EPA in 2006 with ozone allowed trees, and the first time the trees are allowed to be listed in state implementation plans. And I believe Maryland has done it, Virginia has done it, and California is doing it also. It's trying to put trees in their state implementation plans. Right now it's listed under voluntary or emerging and voluntary measures, and there's a cap on the percentage you can get, but it's opened the door somewhat for trees. I think the cap is at 3% that you're allowed to take. Part of the issue is trees grow and die, and there's no certainty they'll always be there, so we're trying to work with the EPA now to figure out how to get these in the plans. But the evidence is there that trees can improve air quality. Now the next move is how do we get trees into these state implementation plans so that trees are, in essence, become, if you get it into the state implementation plan, it becomes more regulatory. That you're forced to do it. If you say you're going to do this in the state implementation plan, whatever it may be, I'm going to increase tree cover, I'm just making this up, by 5%, and that's accepted within the plan, you have to do that, because now you're bound by statute of that implementation plan to do that. So it moves trees from this nicety of saying, well, trees are good because they improve air quality, but into the regulatory phase through the EPA saying, we're going to use trees to improve air quality. And I know they're doing this in Sacramento to try it, in Maryland, they've tried it in Houston. We need to work with the air quality regulators to try and do this. But there's a chance to do this. It's not a perfect system, again, because trees can grow and die. There's various uncertainties and various about the impacts on species, but the door is open here to keep doing this. Hi, David. David says, will future versions of iTree place greater weight on benefits of trees, on their placement along the streets and parking lots, for example? The answer is yes. In iTree, we are working on spatial distributions relative to sources, and we have a new air temperature model that will be a spatial map. Design might be able to do that also. Design looks at small-scale issues in the landscape. Landscape works at large-scale issues. So we are working on this issue because location becomes very important on some of these. I just threw this slide in here. We talked about air quality today, but remember there's also, no matter what design you do for the price you pay, there's multiple other benefits that come from this, and also don't forget there are costs associated with it in terms of maintenance and things such as pollen and maybe possible increased energy use. But it's not just about air quality. There's many things that come back from this. So, summary, over 100 million people in the U.S. are affected by poor air quality. Trees can be both positive and negative in terms of effect. The general trend is improved air quality due to pollution removal and reduced emissions. Trees can be used currently in a limited fashion within these state implementation plans, and that trees again provide multiple benefits at no additional cost. So we want to consider that in our designs. Sarah, hi Sarah, has a question. At NAS workshop in February, the EPA gave indications they might be open to using trees as a non-voluntary measure. That is true. That's why we're trying to work with them. The question is we've got to get it into that, and the more nationally you hit the regions saying this wants to be done and trying to work with this, it's done at the regional level. It's trying to have the science and the certainty that if we're going to do it, you don't want to put it in there if it's an uncertain device, because the consequences are quite significant in terms of human health if we make mistakes in these state implementation plans. But we want to work through this process and try to figure this out. And that's what we're working, some of us, Gary Allen and many others, myself and others, trying to do this with the EPA and just trying to figure the mechanism how to do this. Hey, hi Chuck. How easy is it to run an iTree data set through BenMap? You don't have to. Chuck, the new version 5.0, has BenMap already in it. We spent over a year running every county in this country, so it's already preloaded. BenMap's a great model, but it does take some time to learn. So we loaded it in there already. So I don't know if there are any other questions or questions that I missed. I think that's the second last slide, any slide that I have. Hi Faith, does your work consider possible impacts of non-native pests which can wipe out a city's tree canopy in a few years? Yes, iTree does that. Again, this talk was just on air quality. iTree has 30 or 31 pests or killers, the maps are already loaded in. So what iTree will do, if you collect data on your forest, it'll look at the potential risk of all 31 of the pests, plus how far away the pest is to your city. So if you're in California and you have an ash tree, you might have a risk emerald ash borer, but it's over 750 miles away. So we color code that out to let you look at potential pest risks. We're also doing potential shifts in species due to climate change right now. We have invasive species lists in the data set now, but we're looking at climate change issues also. But the pests are already in there. It's potential risk, though. It's not saying those trees will die. It's saying what's the potential risk if the insect did the worst that it could do. Just because an insect gets into the city doesn't mean it's going to kill everything, but it shows you a relative risk. The idea behind that is if you have no elm trees in your forest, you're really at low risk to Dutch elm disease. It's that type of premise, but looking at 31 pests, Asian longhorn beetles, a whole bunch of them in there, along with their maps. And Meredith has a question. Oh, from Patricia Joyner. Any research on the role of evergreens and particulate reduction during winter? How about deciduous in winter? Yes, that's taken into account in the model. It has to do with leaf surface area and bark surface area. So in the model of iTree, it knows when the trees go, it knows if the tree is deciduous or evergreen, and it drops the leaves in the wintertime. So the particulate reduction, conifers are the best in essence in many ways, particularly for particles, because they offer year-round protection. They also offer a high leaf surface area, and they often have tiny needles, so are fairly efficient at capturing particles. So there is research on this at the species level from other people that have done in Europe and the United States, but in our model we estimate only for the whole area of analysis, so we do take into account the winter and summer effect of deciduous and evergreen trees. Question from Keith. Hi Keith. The relative difference in VOC emissions may be considerable at okay, typo or something like that. It's my understanding that based on conversation with our state report models that the relative difference in VOCs have a diminished impact on the regional ozone. Oh, individual tree scale. Okay. The relative difference, yeah, at the tree, it can be significant at the tree scale. I mean, an oak tree versus a maple tree during the one tree to one tree will be relatively large. At the regional scale, yeah, because it all washes together. It's not only just the trees; it's also the anthropogenic sources. Like in Los Angeles, that study by Hyder Taha found that the species composition did make a difference, because in Los Angeles it tends to be, because you have the clean air coming in from the ocean, what Los Angeles emits is very important, so species become important at that scale. In New York, in the New York metro region, we shifted everything to all high emitters or low emitters. We couldn't even pick up a blip in the signal at the regional scale, because there's so much volatile organic soup from the anthropogenic emissions and background forest emissions that the urban forest couldn't even be detected. So if you're in the southeast, again, it's all context of scale and where you are. In the southeast, the southern forest can produce a lot of volatile organics, but if I'm in Atlanta, the humans produce a lot of volatile organics at the scale of the city. At the regional scale, VOCs are very dominant, depending on where you are, particularly in the southeast. But as I move into the city, the cars and the factories become dominant too. So it's an issue of regional scale versus local. The other way to look at this too is regional scale volatile organics from the southern forest are a background concentration. What we're not going to do is we're not going to wipe the forest out because they're emitting volatile organics. They're part of nature. The question is, what are we doing as humans in terms of driving our cars and emissions from other sources, and how do we design that? But in a city, we do have choices about species composition and what we plant. So it's just one more piece of the puzzle. Species become important.
Thank you so much, Dr. Nowak, for presenting for us today. We really appreciate you taking the time.